Cool. Well, thanks for having us. Today, as John said, I'm going to talk about some ongoing work that we've been engaged in to develop maps that communicate the extent and frequency of inundation. For the state of Vermont, specifically right now, we're focused mostly on the Lake Champlain Basin, but we'll talk about how we can expand that to the whole state. These maps are being developed with a topographically-driven model that relies predominantly on that LIDAR set John was referencing. And today what I'll do is describe sort of the essence of that model, some of the challenges we've come up against and how we're working to correct them, and then go through sort of a handful of applications for this data because it's being used in a wide variety of ways. I do want to acknowledge Kristen, who is my co-author on this work, and we work closely together on much of this. I also want to acknowledge a handful of students, past and present, Jesse Gorovich, Jeremy Matt, and Scott Lawson and Stephanie Drago, who've been extraordinarily instrumental in pushing these efforts forward, each of which brings sort of something unique to the table, but has also taken these maps and done something unique with them. And I'll touch on a little bit of that, as well as acknowledging some colleagues, Beverly Wemple, Donna Rizzo, and Jarlath O'Neill Dunn. So just starting out right with the why do we need these flood inundation maps? John touched on it a little bit, and what is their value? Well, the obvious answer, right, is that these flood maps depict the extent of likely flooding. This helps to communicate risk to people and infrastructure. And while we have FEMA flood maps digitized for some places in the state, and they're referenced in terms often for zoning and planning, the coverage, right, is not complete. The information is limited. It communicates in a deterministic sense the extent of the 1 in 100-year flood, or the flood that has a 1% annual exceedance probability. And in some cases, or in a lot of cases, you know, these maps are outdated, using information from the 1970s. In some cases, our old understanding of hydrology, etc. The second major use case for these flood maps, and really what most of us have been developing for the application for, is understanding natural processes along rivers and floodplains, and as a result, their functioning. In these types of systems, it's long been acknowledged that the hydrologic regime is king, and by that I mean sort of characteristics that describe the flooding, right? So how often do these systems see floods? What is their duration? What's the timing of those flood events? And a growing body of research is documenting that these naturally functioning floodplains, those floodplains that are really well connected to their river channels, help to improve water quality by capturing sediment and nutrients such as phosphorus, offering flood resilience by storing floodwaters, and support important habitats, both aquatic habitats as well as riparian habitats. And so acknowledging the role healthy floodplains and rivers play in mitigating these water-related hazards, the state of Vermont has sort of dreamt up and is directing the development of the Functioning Floodplain Initiative, which many of you may be aware of, many of you may not be. Generally, it's an approach to map and track the status of floodplains in Vermont. Kristen and I and others listed on this talk as part of the UVM FFI team, or Functioning Floodplain team, are working with folks within the state, as well as consultants, to integrate the current state of the science into this management framework. And these flood inundation maps are critical for so much of this work, but really at a fundamental level, when we think about this FFI and as specifically as a web mapping application, we think of this using these maps to answer, again, some of these fundamental questions. Where are the floodplains within Vermont? What's our inventory? And how hydrologically connected or disconnected are they? And so when we set out to create these maps, we're sort of faced with one of two general approaches. I'm kind of grouping these in a sort of lumping fashion. On one hand, we have these traditional approaches, and this is where the FEMA data sets come from. These typically involve 1- or 2-dimensional hydraulic models, which account for the physics of water as it moves across the landscape. And again, this is sort of a large bin, and so there's a very wide range in these types of models, and therefore their levels of complexity. However, generally, because these are both data and computationally intensive, because they resolve and account for conservation of mass, conservation of momentum at nodes across the landscape. And therefore, they're really hard to apply at scale. And if we want to think about creating these flood maps for all communities, this is not really necessarily a tractable way. Sort of on the other side of the coin, there's these reduced complexity approaches. You also see them called sort of low complexity approaches. And these have been developed within, I'd say, the last decade or so in response to, again, this increasing availability of these robust geospatial data sets, such as LIDAR. We see that with that, increasingly scientists, some managers are also relying on this new generation for inundation mapping. And very generally, these approaches, what they do is they coarsen the unit of analysis. So instead of thinking about water flow and patterns of flow at sort of nodes on the landscape, we break up the landscape into sort of chunks that are similar, and we identify flow patterns within that chunk on the landscape. We also, as the name suggests, we also really simplify the physics, and we reduce the complexity with which we understand the movement and the water patterns across that landscape. For our work, and because of the amazing data sets of LIDAR, but other data sets as well here in Vermont, we adopted one of these types of approaches, specifically the hand-based approach. And when I say hand, H-A-N-D, I'm talking about height above nearest drainage. And so it's basically a relative elevation map. And so what I'm going to do is for the next few minutes go through this approach at a pretty general level, so you can get an appreciation for how we go from a LIDAR-derived DEM to a flood inundation map. And so the first step is to take a DEM, a digital elevation model, and convert it to this relative elevation map, or a hand map. You can see the absolute elevations in this DEM at the top. This is from a paper out of 2018, where you have higher elevations in the headwaters, grade to lower elevations at the outlet. When you convert that to a hand map, the river network shines through. We see these lower bits are the lower elevations, 0 is the channel bottom, and the elevations increase as you move away from the channel. The next step is then to take that hand map and to build a stage discharge rating curve on a reach by reach basis. So again, these reduced complexity models coarsen the unit of analysis, and we use what we call a reach. And a reach is pretty simply a length of river that has similar sort of morphological characteristics. And what we do is take for increasing elevations within the hand map, or stages, or water depths, you can kind of think of it similarly. We take slices through the hand map, calculate all the important parameters for the Manning's equation shown here, which is a really fairly simplistic way of thinking about and representing open channel flow, and use those values to calculate discharge. So again, we do that for increasing elevations, or hand elevations, stages of water depth, to create this stage discharge rating curve on a reach by reach basis. Then we translate that to the inundation maps. And a big piece of this is providing context, especially as we think about creating these maps over large scales. So what is the context of 1,000 CMS? So to do that, we use a flood frequency analysis. And for this, specifically in Vermont, we use regional regressions to relate discharge to the recurrence interval of that given flood event. And so to sort of show how that works, kind of bring it together, let's say, for example, we want to map a 2-year flood, the flood extent of a flood that occurs once every 2 years, or has about a 0.5 annual exceedance probability. Right? We identify for that reach what that associated discharge is for that 2-year flood. Go to our stage discharge rating curve, identify that hand elevation, and then basically fill in all of those cells on that hand map at or below that elevation. So we create a 2-year flood map. We similarly, can move up the recurrence interval. We can go a 10-year flood, we can go a 500-year flood. This approach, there's a good bit of uncertainty associated with this type of approach, and there's really uncertainty associated with all types of flood inundation mapping. But one could argue even more so with this reduced complexity approach. And many are kind of identifying that it does well in certain settings, not in other types of settings. And so we wanted to kind of account for that and communicate that, and not just sort of show that these areas of the 500-year flood are going to be wet and these areas during a 500-year flood are going to be dry, but actually communicate sort of where our certainty is within that range. And so to do that, we took that basic hand mapping approach and made it more of a probabilistic approach. To do that, we account for uncertainty as a result of measurement error, limited data, and process simplification. We coded in a Monte Carlo analysis, identified sort of the range of error or uncertainty around all of our input parameters, or to our best of our knowledge, and ran it 1,000 times. And so we basically come up with 1,000 discharge values that then sample from 1,000 rating curves. And as a result, we get a probabilistic floodplain map that looks like this, right? And so areas that are dark red have a really high probability of inundation during a 2-year flood. And as you move out in terms of lighter colors towards these pinks, we are telling you that and communicating that these are areas that may or may not be wet with decreasing levels of certainty. And so we formalized this approach within a model written in Python, and we called it the prob hand, or sort of probabilistic hand mapping. And I say we, but really Jesse Gorovich, a former PhD student who's now moved on, was extremely instrumental in putting this together. And he and I worked together what I'm calling phase 1, which is sort of this initial round of building out the model, sort of testing it out. For this phase 1, we mapped inundation for Lake Champlain Basin on rivers with a drainage area greater than 10 square miles. And this was about 2,000 river kilometers. You know, as I've been talking about, we relied heavily on geospatial data sets as inputs to this model, mostly, you know, the LIDAR-derived DEMs, but also land use, land cover that has been developed at a very high resolution for Vermont, and took advantage of that really robust and unique data set. We also used the National Hydrography data set, or NHD Plus stream network, to define the reach extents, right? So those units of analysis are being defined by that NHD Plus stream network. And so we sort of carried this phase one out, and then sort of quickly moved on to phase 2, which is sort of, you know, version 1, and now we're kind of moving into version 2, in part in response to the FFI, or Functioning Floodplain Initiative. For this, we're expanding the network to rivers with a drainage area greater than 2 square miles. So we've more than doubled the area that we're working in. So now it's about 5,000 river kilometers we're working to map. We've been thinking about and looking for ways to improve upon our accuracy. We found pretty good results matched to documented flood extents for the first round, but like I said, there's definitely a lot of room for improvement, and there's some errors to deal with, and so we're looking for ways to improve accuracy. We're working to post-process our results to create more functional flood inundation and floodplain maps, sort of for public consumption. And then looking for a variety of ways, this has been ongoing throughout the development of this approach, to incorporate these types of flood inundation maps in research and management applications, and I'll talk about some of those. And so what I'm going to do for the rest of the talk is go through some examples and dig into some of these pieces. So the first is thinking about kind of our reach definition, right? So again, you know, to do this hand-based mapping, we're sort of segmenting the world into these reaches. And our phase 1 relied on these NHD plus defined reaches. And these are really hydrologically defined reaches, where each reach starts and stops with the presence of a major tributary. So you can see there's this yellow reach that starts and stops with these 2 tributaries, and there's a blue reach. We have decided to maybe explore, we did decide to explore what additional reach breaks and additional resolution on these reaches might provide to this floodplain mapping effort. And so again, being in Vermont, we're very blessed with all sorts of data sets. And one of these amazing data sets is the Vermont Stream Geomorphic Assessment, which did many things, but in part has defined additional reach breaks. And so you can see what those reach breaks are. And these are based on sort of a desktop analysis, but also a good bit of field checking and field analyses. And they do it based on channel geometry, valley morphology, or slope, which you can remember are really critical pieces to the Manning's equation, and therefore determining sort of that stage discharge rating curve that defines the extent of inundation. And so, for example, here within this blue reach, this one NHD reach within the SGA defined reaches is broken into 3. And you can see why, right? You have a much narrower valley right here, likely steeper than these other reaches within that one NHD plus reach. So to evaluate if changing to this SGA defined reach was important, we went through a full analysis in 2 watersheds. We call it our pilot watersheds, the Black Creek, and the headwaters of the Missisquoi, and the Mad River and the headwaters of the Winooski. So we created floodplain maps or flood inundation maps using NHD defined reaches. We defined floodplains using these SGA defined reaches. And then we compared those, and we also compared them to hydraulic model predictions, or this traditional approach. And this is just some example of kind of what we were looking at. These purple areas is the 100-year flood extent for the NHD defined reach. The blue is the 100-year extent for the SGA reach. And you can kind of take away, generally looking at this sort of as a snapshot, basically that we found no huge difference in the floodplain maps between NHD and SGA for these 2 watersheds. We also compared those again to the more traditional hydraulic model, and for both of them found very good agreement. However, there were some really interesting geomorphic patterns that started to come to light, and that helps us in part understand the importance of these geomorphically defined reaches, but also sort of how this model is behaving. So for example, I'm not going to go through much of this, but this is an F statistic is basically a way of comparing 2 different maps. So a value of 1 would be perfect agreement between the 2 different approaches to these maps. And what we're basically seeing is in confined valleys where the slope is probably steeper, we do a pretty good job with these hand maps of mapping out the inundation extents. Whereas where the valleys are wider, slope is less in general, there's a lot more error that gets introduced. And so we sort of take this and move on with it. However, while there's a lot of value in these SGA reaches, we ended up deciding not to go with it for a variety of reasons. One of the big ones is of the variable quality of the SGA geospatial layers. It hasn't been fully, all of the great data that's been collected through the DEC hasn't been fully translated into these geospatial data sets. And so we still are very interested in pursuing this route, and I'll talk about it a little bit more towards the end. The next sort of area of exploration that we have been looking into in terms of improving accuracy is part of the whole process of the DEM processing and delineating the stream network and the hand rasters. And so just to kind of go as a little bit more background digging into the details, to go from a DEM to a hand raster, we need to define a stream network. And to do that based on topographic data sets, the stream network and hand raster, we need to go through this hydrologic analysis, which is pretty fundamental and foundational to a lot of different types of analyses. These types of analyses look at flow direction and accumulation and the distance to the stream on a cell-by-cell basis. To get to this point, to do these analyses, you have to actually take one further step, and you have to go through and fill what we call sinks or pits on the landscape. And these are depressions in the landscape that as you route water through a topographic data set, they sort of collect the water, or at least the model, or these algorithms identify them as areas that water would just go to sort of indefinitely. So, right, in reality, right, these fill with water and they continue, flow paths continue through them potentially. And so this is just sort of an image. And so what we have to do to sort of make these DEMs more hydrologically correct is we need to fill these sinks or these pits until they match the elevation of sort of its nearest neighbor. And so here's an example, right? If this is a raster cell, they need to be filled to meet that downstream. So when you actually map the directions and the accumulations within these cells, the model knows that it needs to keep moving downstream. in this process, in the Lake Champlain Basin, right, there's a lot of little bits and bobbles that have been filled, often just a couple of raster cells here and there to make the DEM more hydrologically correct. And these have very little impact on the hand raster. However, we identified 2 areas in particular that actually do have a really big impact because of this need to fill pits or fill sinks. One are associated sort of with an artifact of LIDAR-derived DEMs, right? These are collected from an airplane taking data from above, and so what you see on the ground are bridges. So these areas are road crossings where roads or railroads cross over a stream, and there's a bridge deck or there's a road deck because there's a culvert underneath. And if these aren't corrected for, right, as you run it through these analyses, the model thinks it needs to fill the pits upstream such that the elevation of that upstream cell here needs to match that downstream cell to route the water properly. And so I'm just showing an example of one of these areas here. You can see this area upstream. This is the hand map created right from a pit-filled DEM. The entire valley has been filled and now has a hand elevation or relative elevation of 0. Meaning, again, this whole valley bottom has been filled in that process. When we go ahead and hydro-enforce, remove that barrier that we know doesn't exist, or at least the river doesn't see it as existing, we then rerun the model. And now what we can see is that because this area hasn't been filled in during the pit filling or sink filling process, we now can see that floodplain topography evident in the hand model. That channel bottom, that value of 0, is now just within the confines of that channel. And this is obviously sort of pushed out to the floodplain map, and so I'm showing an example of that here. So this is the 2-year flood inundation extent. The purple is the original unhydro-enforced, without hydro-enforcing the stream crossing in particular. And this gray is when we hydro-enforce it and rerun the model. And obviously, you know, these are very different layers, and this is a particularly extreme example, especially in these sort of low gradient settings, but these definitely exist. And I just want to note that, you know, you might be asking which one's correct. The gray is much closer to sort of our modeled inundation extents through the traditional approaches, as well as observed and documented high water marks after flood events. And so because of the importance of this to our work in the hand mapping, as well as acknowledging that these DEMs are really important, being hydrologically correct for a variety of applications, we, being the UVM sort of FFI team, functioning floodplain team, joined forces with the Spatial Analysis Lab and received funding through VCGI to undertake a full hydro-enforcing effort, starting in Lake Champlain Basin, because again, that's where our focus is at this point. I do want to say, and just kind of mention, as many of you are probably aware, these DEMs that are available through the state are hydro-enforced to a point. The major rivers and the major corridors are actually hydro-enforced, and where the issues lie at this point are in the tributaries. And so again, we started in Lake Champlain Basin in Vermont, that is depicted here, 6 major watersheds, 113 Huck 12s shown here in this kind of lighter outline. We worked at this Huck 12 level. We found both in the flood mapping, as well as we're working at that level to hydro-enforce all of the DEMs. We find it's a really tractable kind of level to work in. We worked with the SAL because they're great at having a student body that is very effective and efficient at sort of these manual processes. While there are algorithms out there to hydro-enforce, by far the best, most efficient way to do it, maybe not efficient, but the most accurate way and most complete way to do it is manually. And so we've been working with 4 students since October. We're 65% of the way through the hydro-enforcing effort and have completed the entirety of the Winooski, and I think are maybe hours away from completing the entirety of the Missisquoi River Basin as well. To do it, the students target areas where the stream is crossing a road, and Stephanie Drago, a former student, is now working for us, has put together a really great data set and has helped manage these students to help guide them through going through and looking at each of these crossings. We estimated there are about 4,300 road stream crossings to inspect within the Lake Champlain Basin in Vermont. Steffi has been doing a spot check when we think about quality control on the completed HUC 12s. And then once we finish a full HUC 8 or a full watershed, we do more of a thorough evaluation on sort of an aggregate of a pit fill DEM at that level. Excuse me. I do want to note Livia, one of the students working with Steffi and working with us on this project, put together a fantastic story map, and it's down here, or I know that's a really hard address to copy, but I'm sure she'd be happy to share it, or I'm happy to share it with you if you want to look at it. Does a great job of sort of explaining and demonstrating kind of the rationale behind their work in this hydro-enforcing effort, and provide some really great examples. And I took a screenshot of it on this lower image, and you can see all of these points are those stream road crossings to be inspected. And you can see on the right, all of these are not hydro-enforced, and there's this cool slider that she included to show what it looks like prior to hydro-enforcing and post, where the students cut basically a notch into the road to allow for the stream to move through and to become more hydrologically correct. So the other thing that we're sort of noticing with the DEM processing and this pit filling that's an artifact are areas of disconnected floodplains. And these are areas where there's not necessarily a culvert and where we don't necessarily expect there to be a place where we would hydro-enforce to fix this problem. So just an example here, this is on the Mad River. We have this whole section of the floodplain here. This is the hand map that is one elevation, and that's because it's been filled in the pit filling process in order to reach an elevation to drain properly out to the river. And this area isn't one elevation, right? This is a floodplain that has some more complex topography. And so Jeremy Matt, a PhD student working with us, is working on an approach to account for this. So in these settings, we can't just sort of cut a notch necessarily, but we could, sort of recondition the hand map after processing. And so he's working on an approach to do that, because we really think these types of disconnected floodplains underestimate the floodplain volume and they overestimate flood inundation extents, and so they provide an additional source of error. So those are sort of like the within the model things we're working on to improve accuracy. Once the model is run, we're also working on, like I said, some approaches to post-processing. One of them is taking all of the information that we're spitting out in this model, right? The probability of a 2-year flood event, of a 100-year flood event, and of all the different flood events, and aggregating it into one composite inundation map that provides us with a sense of sort of the probabilistic distribution of inundation across that landscape. So that's one piece. Another is there's a lot of artifacts from this type of approach, meaning reach-based mapping. When we segment out the world, it comes sometimes a result of that is that some of the flood inundation maps and some of the results are also segmented. And so there's an example here when you have a small tributary coming into a large river, you actually negate some of that floodplain. And Scott Lawson, a master's student working with us, has come up with a pretty slick way of post-processing those results and getting that information back. So kind of moving on finally to thinking about some of these applications, right? So we've got these maps, we're cranking them out. What are some of the applications? Well, right, as a baseline, this information is serving, again, as a base map for the functioning floodplain initiative, like I talked about. And so this is just kind of an example of what we might see within that application. This is a composite floodplain map. We're using it for a variety of different pieces of information, informing us on different types of processes in general. But one of the things in the FFI is looking at sort of the full extent of the floodplain. So we're using the 500-year flood, 5% probability as a way of saying this is the full area. This is potentially how much floodplain we might be able to gain if we restore process in this area. We're also using it to gain a better understanding of the hydrologic connectivity of certain settings here in Vermont, using these floodplain maps to do that. Like I said, there's numerous other applications. So one of them is another piece of work I've been engaged in, looking at floodplain deposition patterns. Right, so one of the benefits of a properly functioning floodplain is capturing sediment and nutrients, specifically here in Vermont, or at least the Lake Champlain Basin, we're interested and concerned with phosphorus. And so we've been monitoring a handful of floodplains throughout the basin for the deposition of sediment phosphorus following flood events. And what we're finding is the inundation frequency of that floodplain or of that certain setting is really important for determining that phosphorus deposition rate. So as you would imagine, right, areas that are inundated more frequently have greater sediment and greater phosphorus deposition rates. And so we've been quantifying that. And this type of information, along with these hand maps, can be used to extrapolate the information we're collecting sort of at a plot by plot scale throughout the basin. Other applications, Jesse Gorovich, who worked on sort of the first phase with me, used these hand maps to evaluate changing flood risk. And by that, I mean how these flood risks throughout the Lake Champlain Basin are changing with climate change, but also how we might mitigate them with some restoration interventions. And also what the distribution of these flood risks are to different socioeconomic classes. Steffi Drago, in her master's thesis, quantified floodwater storage using these floodplain maps to think about kind of where within these watersheds can we store or are we storing more water, and thinking about sort of the flood resiliency impact of a properly functioning floodplain. And I have to say there are many, many more that are currently ongoing and that could be conceived of using these types of maps. You know, within the FFI, we're also looking at sort of mapping habitats, and Liz Duran at UVM is thinking about using these and exploring ways to use these inundation maps for that, as well as many other applications. I just want to sort of put this somewhat cautionary note out there when we think about applications, because inevitably this is probably on some of your minds and it's a question we often get. These types of maps, at least, and these types of mostly, you know, the maps we're creating can be used sort of for this general evaluation of flood hazards, but I caution that they're not yet useful for flood risk management, specifically at the property level. Right, Jesse did sort of an exploratory analysis kind of at the aggregate basin scale. And so they aren't at this point going to replace our FEMA flood insurance rate maps. They at some point might, but the National Water Model, which is experimenting with adoption of these hand-based approaches to provide inundation forecasts and sort of emergency management. And so there are sort of these opportunities to use it in terms of evaluating flood hazards and flood risk, but at this point, they're not necessarily a replacement for FEMA maps. So for the last little bit, to kind of round it out, I'm going to talk about, you know, there's a lot that we can do to improve upon these maps, and there's a set of wishes that we would, you know, especially speaking to this community, think about where we can go to continually think about improving this data set and making it accessible and available. So like I said, we continually talk and think about how can we improve them. So I'm just going to run through a few of them. We want to better constrain our uncertainty. We know there's a lot of uncertainty in this, and we've documented some degree of it, and we've incorporated it into our process. But we know that we can better constrain that. Remove artifacts from the reach-based analysis. So again, there's all of these artifacts that remain within these maps that we would like to continue to kind of improve upon. This approach takes, again, this sort of reduced complexity view of the world and sort of simplifies hydraulics. And this works in some settings, it doesn't work in other settings. And so we, Kristen and I in particular, and others have been thinking about ways to sort of reintroduce a little bit of hydraulic complexity and maybe parameterize that without going full bore and slowing down this model. Specifically thinking about how we might be able to partition the flow between the channel and floodplain and really kind of come up with a little bit of more robust kind of volumetric estimation. And there's actually some exciting work ideally coming down the pike that might be able to help fund some of that. I didn't know if this is a great place to put it, but I do just want to put a plug that we are working and hoping to sort of make all of this publicly available, right? The hydro-enforced DEMs, as well as our floodplain maps that we're working to finalize and make them available to the public. And that's been sort of an important piece of this through the Open Geodata portal. So on to a few of these wish lists. So kind of coming back to the SGA geospatial data sets. Again, these data sets, in terms of their representation, their digital representation, aren't 100% complete, and they have varying spatial coverage. And so we would love to make this, make our inundation maps sort of more consistent with the SGA data. This would make them more geomorphically relevant, more consistent with the FFI work that we're doing. And so hopefully sort of we can undertake this effort to better translate that. Also, sort of on the Dear Santa wish list, water penetrating LIDAR would obviously be amazing. The uncertainty introduced by LIDAR and no topography within our DEMs below the water surface introduces a good bit of uncertainty, and we know it has, and we've quantified this to some degree. It introduces a certain amount of error in our inundation mapping. And again, we're coming up with ways to sort of work around it and quantify it in different places within the basin, within the state. But if we really, just didn't have to put it in the uncertainty category, that would be pretty cool. And then finally, why not continue to push this out to the rest of the state? So as I've talked about, we've been mostly doing this initial effort in the Lake Champlain Basin, driven by sort of initial efforts funded by the Basin Program, and the focus of the FFI right now in the Lake Champlain Basin. But we would love to expand this work, hydro-enforcing work, as well as then the floodplain mapping that those hydro-enforced DEMs would lead to the rest of the state. This would help, this would help expand the FFI if that becomes available at any point, assisting with planning and tracking to address the TMDLs within the state for phosphorus here, the work we're already doing in Lake Champlain, but also Lake Memphremagog, potentially help, address nitrogen TMDL in the Connecticut River Basin, and then statewide issues and concerns about flood resiliency. The one sort of final note I want to leave on is that this approach, with all its warts and all its issues, and is really exciting for the state of Vermont, in part because I think because of the low complexity of it and because of the minimal amount of inputs that are required, it can be highly responsive to our changing landscape and our changing environment. So once we get this up and running and once everything's in place, there's nothing to say that we couldn't every year create new inundation maps, right? And therefore be looking for these changes in inundation across the landscape. Look for changes in, as inputs changes in hydrology, changes in the landscape and the land cover, and et cetera, and track that. And so that's kind of an exciting piece that, those more traditional approaches don't necessarily have because of how hard they are. And so I see that as a really exciting opportunity. So just kind of wrap it up with just, a bunch of thanks. Lots of funding on different pieces of this. It's been had taken on a variety of different iterations over the past 2 or 3 years. As I said, many students have contributed and been extremely instrumental. The Spatial Analysis Lab has also been very gracious in helping us specifically with the Hydra-enforcing effort, as well as John and the staff at VCGI. And yeah, with that, I can answer some questions.
Thank you so much. My mind is blown. That was amazing. And also want to just take the opportunity to thank all of those involved in getting the resources to make wall-to-wall LIDAR available in the state of Vermont. Without that, I don't think this would have been possible. So, Agency of Transportation, Regional Planning Commissions, and of course the USGS and their 3DEP program. But with that, why don't we open things up for questions? I know we have one from Ned Swanberg here. How possible would it be to use underroad culvert location to hydrologically correct the DEM further?
Yeah, I mean, I think we are using it as a reference point. And, Steffi, feel free to jump in because she's been way more engaged in the management of that. But we are using it, again, as a reference point. I believe that, and Kristen might be able to speak to this, I believe that Stone has used it as sort of a way of automating that process. And so, that there is some synergy there in terms of that approach.
Yeah, in a discrete location, I think they used it in the Winooski Basin. Okay. I'm wondering though, Ned, are you talking about actually representing conveyance under the road in the DEM as part of this hand modeling approach?
Yeah, that was the thought, because a lot of times roads are creating, barriers to water flow down hillsides and so forth, and misconstruing quite what the pattern should be.
Right. Yeah, I would defer to Rebecca on that, but I think it could be a little computationally challenging and require lots of post-process or pre-processing of the DEMs.
Well, if I understand correctly, we are, right? So if there's a culvert, if there's a road crossing a stream, we take that out so that the DEM knows to put the river in that spot. Is that, I don't know if that's helpful.
Yeah, but I'm actually doing the next level out, which is to say a lot of roads just have simply dry culverts, no stream, just local drainage from from the drainage system, from the ditches and such, and ditch extended hydrologic network and so forth. That's complex and problematic all by itself.
Yeah, it is, and I think that's again somewhat speaking to obviously not exclusively, but these things show up even more in urban areas, and that's definitely not a place where this approach is necessarily going to shine, where there is a lot of sort of underwater or underground, flow, and some of these sort of culverts that might make it a little bit more complex than these DEM-based approaches might be able to handle.
We have a question from Pam as well. Can you talk about what materials sample collectors were used for determining the floodplain deposition?
So we have floodplain monitoring sites set up throughout the basin, about 20 now, and we put out actually just artificial turf pads as surface markers that help us determine how much sediment and associated nutrients are deposited following individual flood events. And so, yeah, it's pretty low key. It's just sort of astroturf out there at this point.
That's great, thank you. Yeah, I did something like that with my thesis years and years ago, so the method has improved widely, so I'm glad.
Did you do that work here in Vermont?
Yeah.
Oh.
Yeah, UVM and the La Platte watershed.
Oh, okay, great.
And we had Al Cassell and I, bless his soul, we had a hard time finding really good materials that would keep the sediment and be able to quantify it out. So
what did you use?
It was this thing. It was like something we found. It was like a coil. It was like a coil material that was plastic but embedded within like a filter fabric. Huh. And we were able to capture the sediment enough because we were having a hard time finding something where the sediment wouldn't just wash off of it, and it captured it enough because it was like almost like curly hair but plastic. And then we were able to bring it. It was like in square feet sheets, and then we brought it back and washed it out and measured the phosphorus. So, but these look like what I saw on your slide. It was more like a nice chunk, like really distinct.
Yeah.
So,
yeah, I'd be curious to reach out to you because that would be interesting data. I didn't realize. Cool.
Yeah,
Thank
it's
you.
in the UVM thesis library. We never got around to publishing it, unfortunately, but it's there.
Great, great.
Do we have other questions? If people want to raise their hand in the chat, and you can call on them. I know there's got to be some. I would have expected like 10 hands to go up here. Ned.
So I just noticed, this is probably irrelevant, but you guys are so all over the LIDAR that you'd know, but I noticed a weird feature the other day. I was looking at local flows over dams here in Montpelier, and the break lines were misplaced. They're a tiny bit upstream of the actual dam. And so the water is actually cascading, through the dam. I don't think it's making any difference to the analysis you're doing, but would these kinds of auto-generated break lines affect your analysis in other places that might be worth looking at? That's a big question.
Yeah, I'm not sure. I mean, with the dams, we've been cutting little notches in them just to kind of keep the flow path kind of on par. Otherwise, it usually goes around the dam through the hydrologic analysis, right through the kind of DEM-processing. But I know that's not exactly what you were asking, and I'm not sure. I don't know if you have thoughts, Kristen.
Yeah, so Ned, you're actually seeing in the hydro-enforced DEM product a channel that's been carved around or through the dam?
It's pretty minor, and I don't want to get carried away on this, but I'm looking at the contours, actually, the 1 foot contours derived from LIDAR. And as it approaches the dam, the water is cascading basically through the structure itself, instead of going over the lip and then creating a beautiful waterfall. It's actually a waterfall through the dam. And so I'm just curious, and I'm just wondering if these break lines, as they were created, are worth looking at in other places just to make sure they're not doing something screwy. But it's anyway, just a weird question.
Yeah, we are, as Rebecca said, we are looking closely at the dam. We have the emergency dam layer overlaid as well on our data sets, and we're looking closely at those and trying to make reasonable judgments about whether they're run-of-river structures or not, and hydro-enforcing them accordingly. But yeah, we'd have to ask Steffi and Scott Lawson, who have been more directly involved in some of this hydro-enforcing work, to know if there's been similar kinds of issues at other dam sites.
I do just want to say this. It's a good point when you bring up the dams. Is that again, this approach it's not going to perform well like in the area behind the dam. And so one of our post processing, I didn't mention this, will be to sort of mask out any of the dam affected reaches to say that, you know, we aren't creating a floodplain map here. This is not applicable here. So at this point, the way we're handling the dams and seeing them is, again, just making sure that our stream network is connected through there. So.
And that's an approach that's pretty consistent with the stream geomorphic assessment approach as well. Any impounded reach was exempted from that assessment because waters are not behaving in a fluvial fashion through those impoundments. They're more lake-like. And so, yeah, post-processing step is just to basically mask out those impounded reaches.
Here's another question about the product. When you're talking about putting up the flood mapping product on the VCGI Geo Warehouse, will that be vector or raster? And if it was raster, would it have multiple analyses at the, you know, the 2 and the 10 and so forth, so that you could click on a cell and get multiple information about it?
To be determined. This is an ongoing conversation for us. In part, you know, it's the type of information we need to communicate and want to communicate first and foremost for the FFI, but then also thinking about and having considerations for the size of the data. And so while it would be amazing to, you know, have all of the information in a raster-based format, we'll have to see kind of if that is feasible. But it will communicate, it will have some communication of the variability, right, of frequency of inundation, right? So it won't, the idea here is that it's not just a 100-year sort of single deterministic map, and that there will be some indication of kind of the probability of inundation across the landscape. You can put in your requests, but we'll see.
Thank you.
Yeah.
There were some comments earlier in the chat stream from Rebecca Pfeiffer and others talking about how useful that kind of a product would be, just to have a better sense for across a landscape, where are the areas with a greater probability of inundation for any given event. So hopefully it would be nice to be able to make available those kinds of data sets.
Yeah.
I imagine we'll have a lot of questions around, I think, people excited to use this and unsure on how or whether they should be using it. And I suspect that'll probably be an iterative process as we start to hear about more potential use cases from different people, and whether or not that's applicable. It looks like Jess Robinson has his hand up.
Yeah, sorry for the late question, but it just got me thinking, being that I'm centrally concerned with the past, and you're modeling and you're looking at probabilities, which is interesting because, like, the floodplain maps only center on the current channel. And so does your probability take into, count like old channels and oxbows when you're trying to figure out like what the 500-year probability is, or is it still, are those go into the, I forget what it's called, but the matrix you were using, or the equation?
The Manning's equation?
Exactly, yes.
Yeah. Only in as much, right, as they influence the topography within that reach, right? So a dynamic channel is going to create really different topography that's going to have a really different stage discharge rating curve. And we are trying to also incorporate some more other process-based information into our uncertainty analysis that takes sort of that rating curve and adds, again, those bounds of this is within the range of what we're looking at. And so, you know, a really dynamic channel might it might show up in that regard again because it creates a really different topography and it creates a really different type of channel that we're taking into account with that probabilistic approach. But other than that, historical data isn't really coming into play. So this isn't, this is a current flood inundation map, and so it's not like a river, like a meander belt sort of analysis where like this is where the river might be and therefore this is where it might flood. It's sort of, these are the features that exist today, and this is sort of the likelihood of being inundated.
Okay, great, thanks.
Yeah.
I think Rebecca said this, that your point about this being an easy process to repeat, that if we do see major changes in channel, it can be remapped relatively easily.
Mm-hmm.
Yeah, that's the goal, right? That's the that's the idea that we would love to get to, is that we can kind of recreate it and it can become, sort of like, right, we hope LIDAR to be at some point of getting that pretty regularly to map changes, land use, land cover, how we want to be updating that every few years, right? Ideally, we update this every few years, again, to sort of get a better understanding of those changes in inundation patterns, which really integrates all of those other sort of changing geospatial data sets.
Yeah, just like after Tropical Storm Irene, we had individual LIDAR flights of certain heavily impacted areas. I could envision, flights over those kinds of disturbed areas after the next major flood. And theoretically, we could fairly rapidly turn around these improved estimates of floodplain inundation after major channel changes like that.
Mm-hmm. Yeah.
So it's 10:29, and I know some of us have to jump to 10:30. So I think we'll wrap things up here, but folks can follow up with other questions, and we can send them along and see if we can, Rebecca and Kristen can follow up with any answers there. I'm sure we'll have, this isn't the last we'll hear of this project and this work. A lot more to come. Thank you again so much for taking the time. I think this is amazing. And also thank you for publishing your work in open source journals that we outside of academia really appreciate, because we don't have access to a lot of those other resources. So wanted to mention that. So with that, thank you so much.
Thank you all.